Adam Ward here. So in preparation for this video, you should have watched the Introduction to Modeling and Similitude, which is about an 8-minute clip just to describe what we're up to. And what we're going to proceed with now is our first example about modeling and similitude and how these principles might have been useful in some past decision making. So we're going to start with an example that's about fluid flow past bluff bodies. And for your purposes, a bluff body just means something that's not streamlined. So any fluid flowing past any fixed object, really. And so whether this happens at the extremely small scale, like you see on the left, or an extremely large scale, like you see on the right, we actually get the very same phenomena here. When fluid flows past a bluff body, like the island that I'm highlighting on the right-hand panel, we get these alternating vortices that get shed. If you've ever been in a building that has some structural vibration or some systematic sway to it when the wind blows, if you've ever heard telephone wires or electrical wires seem to be singing when the wind blows, what you're hearing is these alternating vortices kind of attaching to and then kicking off of these bluff bodies. This happens at all sorts of scales and is a really classical phenomena that people study within fluid mechanics. So the example that I'd like to show you that's a little more applied is the Tacoma Narrows Bridge. And so if you're not familiar with the Tacoma Narrows Bridge, this is a large bridge that was built surprisingly to cross the Tacoma Narrows. You can Google and find more, but what I want to show you is what happens to that bridge as wind blows past it. And so this is actual footage of the Tacoma Narrows Bridge, and those shedding of those alternating vortices is causing this bridge to oscillate. This is exactly the same process that might cause that singing sound to appear from telephone wires. It's the same process that that causes these vortices to form and be shed from the islands. And it's one that caused huge problems for this Tacoma Narrows Bridge and required pretty expensive and intensive solutions after the fact. So the question then that motivates us is, how does this happen? And what if we wanted to learn something about this? So what you can see here is at the bottom of the screen, we've generalized the idea of a beam with wind flowing past it. So think of that velocity and that set of arrows as representing wind, and our beam with dimensions h in the direction of flow and d in the direction perpendicular to flow. Let's see if we can describe the way that fluid interacts with a bluff body and the oscillations that result. And so the idea here is that for the prototype, meaning the real world, the full-scale conditions, we know that we've got a beam that's going to be about 0.1 meters in depth and 0.3 meters in width. We know we've got wind at 50 kilometers per hour, and we'll assume that's air at standard temperature and pressure. And in order to learn about that system, and perhaps what the designers of the Tacoma Narrows ought to have done, we'd like to do some scale model testing. And so we can, for example, obtain scale model parts at a thickness of 20 millimeters, so D of 20 millimeters. And rather than test this in a wind tunnel, we're actually going to test it in a water tank. And so we want to test it with a different fluid moving past the beam. So you have two tasks here. Task one is what size model should we use? And in particular, how wide should that beam be, HM? And what speed should the water flow past it, VM? And then secondly, let's assume that we did the modeling and our model had an oscillation of 49.9 hertz. What oscillation would that be expected to lead to in the prototype? Just to make sure we're all on the same page here, that lowercase omega is frequency, and it has units of hertz, which are per second. So 1 over time are the fundamental units associated with frequency. All right, step one of this problem is dimensional analysis. So in the problem setup, we were given some of the information that we need, and you can see here I've got the geometry of the problem, the external effect of the velocity, and the fluid properties. And using Buckingham's pi theorem, we can come up with this non-dimensionalized relationship. Now, I want to note here, I'm not showing the work, but this is a great opportunity for those of you who need more practice with Buckingham pi theorem to make sure that you can recover the same pi terms that I've recovered. And just for those of you keeping track of this stuff at home, yet again, Reynolds number shows up as one of these really critical relationships between moving fluids and bodies that are moving through them, or that fluid is moving around. So that's our non-dimensionalization step complete. And in the future slides, I'm going to refer to these pi terms as pi 1, meaning the dependent pi term, pi 2, the one shown in the middle, the sort of ratio of width to depth of that bluff body, and Reynolds number as pi 3. So our first task was to find the geometry and velocity that should be used in the scale model. So let's start with the geometric piece. Looking at our pi terms, the easiest one that will have a depth, or a width h in it is pi 2. And so you can see I'm setting pi 2 for the model equal to pi 2 for the prototype. In other words, depth to width for the model on the left-hand side should equal depth to width for the prototype on the right-hand side. Now from there, I can plug in the given information. I know I have a depth of 20 millimeters in the model, and I know both dimensions for the real beam. Now, one thing that you can always confirm here, and should confirm, is that the left-hand side and the right-hand side are both unitless. Now, that's a little bit troubling to some people out there, perhaps, because you see I've got millimeters on the left and I've got meters on the right. But in fact, the left-hand side is millimeters per millimeter, and the right-hand side would be meters per meter. So both sides are unitless, and we can set them equal to one another. So you really need to be careful with your units here. The safest thing to do is convert everything into the same units. So perhaps you would pick kilograms, meters, and hours. But you can sort of check your work and make sure both sides are unitless, and this will work out just fine. So solving this, I get HM, or the width that should be used in the model, of 60 millimeters. Now we're going to do something very similar to find the velocity that we should use in the model. So we'll set pi 3 for the model equal to pi 3 for the prototype. In other words, Reynolds number for the model should equal Reynolds number for the prototype. And we can go ahead and look up values for the fluid properties here for water in the model side of the problem and air at standard temperature and pressure in the prototype side of the problem. All right, and we can scratch this stuff out. So on the left-hand side, I've got the density of water in the numerator, the velocity of that water in the model, which we don't know, and the depth that we're going to use in the model. And in the denominator, I've got the viscosity of water. And similarly, I can fill in the right-hand side using the information about air and the prototype. So note here that prototype velocity was given in the start of the problem. So we know that this is how many meters per second the wind speed will be that we're trying to model. And one thing that you might have noticed, and I've just written in purple, why not millimeters? Right? How come just above that in orange, millimeters were fine, and here I'm down to meters? Because I need that left-hand side to be unitless. So it was fine up in black writing when I knew it was going to be millimeters per millimeter. But here, in order for the non-dimensionalization to work out, in order for all the units to ultimately cancel, I needed to use meters. So again, the key thing is that each side of that equal sign, you ought to be checking each time that the units cancel out. So solving that problem, I end up with a model velocity of 4.8 meters per second. And you can see I've written that in the bottom left since I ran out of room. Okay. Finally, we're asked what oscillation do we expect to see in the real world when we do this? And so I'm going to take that first pi term for the model and set it equal to the first pi term for the prototype. In other words, frequency multiplied by depth over velocity in the model has to equal that same relationship in the prototype. So we can go ahead and plug in the numbers that we were given. And again, this 49.9 hertz, this was given. You'll recall in the project setup that I said, assume you've done the experiment at the size and velocity that you needed, and you observed 49.9 hertz. So from here, you would predict that in the real world, in air with the specified velocity, that this would be the oscillation rate, about 29 per second. So I find this stuff pretty awesome, right? The idea that this tiny model in a tank of moving water can somehow inform the way that this full-scale beam is going to work with fast air flowing past it is super cool. And in this example, I want you to notice that it is absolutely fine to switch fluids. So you don't have to use air when you're studying this. In fact, airplane design, car design, for example, in your head you think of maybe wind tunnels where full-scale models are constructed and tested, but actually a lot of smaller scale modeling is done in water tunnels, basically little tanks with flowing water, because it better satisfies these scaling relationships. It's easier to control that fluid in the lab. All right, folks, so that was our first example of using this idea of modeling and similitude to use model results to make a prediction about what will happen in real life. Thank you for sticking with me. Coming up next will be one more video that's got an exercise where you all can work through it in parallel with me showing you some of my answers. Thanks, everybody.